Hear me?
Yes, we can hear you, sir.
Hello, good afternoon. My name is Sahil. Today I will present the next tutorial in few minutes. I am a data scientist. I work with Infineon Technologies. I work. I'm basically from India, and I work for Infineon India. Um, the Just let me know. I will share my screen. So can you all see the screen?
Yes.
So I started working with Infineon around 2 years back. I was a fresh graduate, computer engineer graduate, and within Infineon, when I started, I directly started working on AI topics, and we were able to successfully build a applied machine learning team within Infineon from scratch. Uh, I would say earlier there were not many things or um, that that was being initiated within Infineon. So we took AI as a hot trending topic, and we tried to initiate many topics in the same field. So today I am presenting one of the topic which we did um, on the EDA design cycle. So just let me know when I can start.
It's time to start, sir, if you want.
Okay. So once again, very good afternoon to all of you. Today I will present my topic, which is congestion prediction, deep learning on chip design enabling system. Me, along with my colleague Jaskaran, we developed this solution by watching out the problems that are faced in the EDA cycle. Before diving into topic, let's see the agenda for today. First, I will talk about AI trends in semiconductor industry, how AI has taken over or how AI is booming in the semiconductor industry. What are some of the benefits that are associated with it? How AI is enhancifying the performance of uh, semiconductor. Then I will talk about what was the exact problem statement in the physical design cycle, and then we will talk about what was the solution that we proposed. We will also talk about the flow, that how we trained our model and how the testing was done. Finally, we will look upon to the results, what was the performance, what was the accuracy that we achieved from the traditional method point of view. Finally, I will conclude my lecture. So let's look into the AI in semiconductor industry. So I present a small research that is done by McKinsey, and the source is being taken from various semiconductor pioneers. You can see at the very below of the slide, Cisco Systems, IC Insights, and many other semiconductor pioneers are there. So this study simply states the growth of AI versus non-AI in the semiconductor industry. The survey is for the year 2017 2020, and they also predicted what is going to be the growth for the year 2025. In the first chart you can see the total available market in $1 billion. um, Non-AI market has also increased time to time, but I would say the AI growth was much more significant, as you can see here. So non-AI growth increased from $224 billion to 295, whereas the growth for AI was almost twice. In the second chart, you can say the same thing, but basically in the percentage mode, that AI was how AI percentage increased for the overall industry. After concluding all these surveys or results, we found out that the non-AI growth was just 3 to 4%, whereas for the AI, the growth is going to be significantly around 18 to 19% from 2017 to 2025. And the improvement is significant enough. It's almost 5 times that of non-AI. With the increasing trends, we have also find out some many areas where AI is being applied or researched upon. There are many exciting topics that are happening all around. So from the internet, I searched through many topics and written few of them here. You can all see in each step of physical design, in each component, the research is being going on. For example, in synthesis, we are trying to find out uh, the results estimation, the quality of results that are generated after high level synthesis, auto tuning of high level synthesis. In the planning phase, how we can earlier detect the timing failure issue at a very early stages of floor plan. We do not want to go shift right, we want to move shift left. uh, Power estimation in planning in ASIC designs and so on. In placement, we want to find out macro placement, how a chip can be automatically placed, and what are the benefits associated with it if we place a chip at a particular area. In routing, which is actually one of my topic that I am going to present, which is congestion prediction, the routability prediction, the traffic prediction, how the chip how much is the chip congested after you have placed everything, and finally the timing and sign off. So we want to find out the delay in sign off timing, and so many things. So you can all see a lot of things are happening. With this, why are we even trying AI? Are we complicating more things? uh, is there any benefit, is there any real benefit associated with AI? The traditional approaches are well good enough. They are already providing us with good amount of significant results. They are almost accurate. Then why are we even evolving or involving AI in semiconductor industry? uh, so these are the questions that actually everyone asks when you start, even when you start a new topic in any of the industry. These questions are uh, definitely there to be answered. So, I am not stating that AI will fully take over the semiconductor industry. There are traditional approaches that will still remain, but AI will only assist the human to reduce the overall turnaround time of your product, of your chip, of your design, of anything with what you do. AI will assist you with much major insights that might not be thinkable. So AI assists a human in a way that the product that you are launching um, is completed much faster. So the time to market increases. Once we all know, with reduction in time, there are many costs that are associated with the project. So once time is reduced, overall cost of the project also reduces. Uh, Nowadays, many companies have come up with the AI characteristics or AI as a feature in their traditional product. I could think of Synopsys ICC compiler tool. They are using the AI as a feature with their product. So it also brings along many capabilities as a additional characteristics. Definitely, they amplify the human decision. So maybe the thing that you get to know after 2 weeks of time or after 3 weeks of time, maybe AI can give you some estimation, maybe around 60-70% uh, in a matter of seconds or in a matter of day. So it definitely amplifies the human decision and can fully shift your approach to complete left side. So what was my problem statement and how is it associated with the physical design cycle? So in physical design cycle, we first get a specification on what type of chips we need to design, what should be the final uh, performance that the chip is going to deliver to us. Keeping all this specification in mind, we generate RTL code for synthesis. Once synthesis is done, we get the gate level netlist, and finally we reach to a floor plan. Now this floor plan is then feeded into an EDA tool to find out how much congestion is present in the floor plan. If the congestion limits are permissible, then we do the timing and sign off thing. But if it is not permissible, then we need to replan the or redesign the floor plan. Again, we redesign the floor plan. Again, we try to find out the placement and routing. Again, we check the congestion limits. If these are permissible, then we move forward. Otherwise, the cycle continues. This whole cycle takes around 2 to 3 weeks of time, depending upon the design complexity and depending upon various another factors. So when the floor plan is designed, the designers they rely on their experience, on their past experience, uh, to tell okay that how much congestion is going to be there. But not everyone has that knowledge, and also the designs are changing a lot. The technology is changing rapidly year after year, so it's pretty hard to judge the corresponding congestion that we are going to get at the end of the day. So accurate congestion prediction in the design implementation cycle is a very big challenge. Again, EDA does provide congestion, but the congestion that we get at a very later stage of the cycle. What we want to do is we want to find the same congestion or at least the same hotspots of congestion at a very early stage of floor plan when we do not have much of a parameters around with us. We just have some basic stuff or basic parameters with us, and with that we get some knowledge that okay how is the congestion going to be at the end of the day, so that the changes that one is going to do at the very end can do it much earlier. Also, here I have mentioned some of the problems that are associated with the EDA tool. Uh, with the EDA tool, if we do not, um, there is a very high probability to reset the floor plan. Generally, the whatever floor plan one makes, this has the higher probability of reset. One generally, it's a in traditional approaches we have seen that we cannot get the perfect congestion or permissible congestion within a very few stages of floor plan or within the few attempts of floor plan. Uh, Again, it requires 2 to 3 weeks of rework if the congestion is not permissible, and approximately 30% of design runtime is spent upon routing stage. So it's a so 30% is a huge amount of time that is spent just in routing stage. So we want to reduce this time as much as possible. Again, I am not trying to say or I am not claiming that we will replace the EDA tool all along. Basically, the iterations that we do with the EDA tool might be decreased. With this, we actually save a lot of cost also based upon licensing and all other things as well. So the final question we are trying to solve is that how can accurate congestion be predicted at very early stages of floor planning? Okay, so how we tackled the problem, how we were able to solve this problem. So we designed a computer vision deep learning based approach where we take a floor plan image and a corresponding congestion image. We also considered some additional design parameters that are cell density and pin density. Uh, Please mind it that for training, we took the previous data set that has already been released or taped out. So we have the corresponding floor plan, we do have the congestion images, and we do have the design parameters as well to do the training of the of the model. Mhm. So yes, so with this proposed solution, the benefits that we are going to bring to the designer is that once the hotspot areas are provided very early or very initial stage of floor plan, uh, the designer can automatically rework only on those areas. uh, with the additional design parameters, uh, we also provide the best and worst case congestion for one floor plan. We will see that how do we provide best and worst case congestion in the upcoming slides. So overall, the significant results of this thing is the lower down of iterations, less iterations, and obviously if the iterations are lower, then the overall turnaround time reduces. What was the motivation behind this solution? How we actually came to know about this solution? So we found this paper, which is image to image translation with conditional adversarial networks. Uh, so this solution was basically a pix to pix translation from one domain to another domain. Um, in these examples, you can see that every input is mapped to an output, and then we try to feed in a test input images, and then we try to find out what could be the possible output of this. In the first image, in the first example, you can find out semantic maps that that are inputted to find out the actual and output in the environment, that how the semantic map could look like in actual environment. So also we found out that the same concept is being applied in various different domains as well. Here only you can see few of the different domains that the things are being applied, and in all these domains we were people were getting significant results. They were getting the state of the art results with much higher accuracies and with no constraints at all, and with also they do not require tons of huge of data that we claim, um, that is generally claimed that AI requires a huge amount of data to be trained upon. Um, Also, after this paper, we tried to find out that whether or not the same approach on congestion prediction, whether or not it has been applied earlier by anyone or not. We found out that there were few of the papers uh, that that were doing the same thing, but they were doing in different domains. We wanted to do this in the system on chip design domain, and also one the major difference between the papers that were historically present and what we were trying to do was the addition of addition of design parameters. Earlier no one has done this type of concept um, where they have provided the user or the designer with the flexibility to play around with the design parameters and to find out the corresponding congestion. Now, the major question could be that why are we even considering design parameters at all? Again, as I said, that we want to provide designer with the flexible options. So, just for example, the designer can know that if I change my cell density from very low to very high, how is the corresponding congestion changing? If I change my pin density, uh, we haven't gone through various different design parameters as well, which were width, pitch. So there are many more parameters associated with the EDA design or SOC design. But the same can be included as well to find out that how congestion is changing. We change in these kind of design parameters so that the designer can have a full picture of the scenario, what is going on. So basically CGAN, or conditional adversarial generative adversarial network, was the overall algorithm or approach that went into building this model. So what happens is, okay, this whole solution is basically based upon convolution neural networks, which take in some input array, and then they give out something in the form that you need. So here there are two neural networks. First one is the generator, and the second one is discriminator. Now they they actually match up, or mm, they actually fight with each other to become better and better every time the data is passed through them. Generator task is to take in a certain image, or I would say floor plan image, and convert it into a congestion image. And the discriminator task is to find out that how real is the generated image. So discriminator takes in a pair of congestion and floor plan, and it tries to tell that whether this pair is fake or real. How closer the congestion, how likely the congestion should be associated with this floor plan. So generator keeps on generating the outputs, and discriminator tries to find out the real or fake thing. The learning from discriminator, okay, that how fake is this, how real is this. Let's suppose discriminator says that I found out that it is 80% fake, that the pair that you have given me is completely fake. So what happens is, the learning from this discriminator, this 80% goes back into generator, and then basically generator retunes itself to to build a better fake image. And so on, the loss decreases. So now next time when the same pair goes in, the discriminator says, okay, now this looks more real. Now the fakeness is just around 60%, and this cycle continues. Once discriminator is completely fooled by the generator, we say that our model is ready to be trained, or our model is ready to be tested upon. How we did this kind of thing, how we consider design parameters, let's look into that. So here is our training flow, where we take the floor plan image, we take the cell density and pin density. Now cell density and pin density were provided to us as an image. So I can also show you. So this is one sample image of cell density. This is how a pin density looks like. We took these images and converted them into a quantitative or qualitative value, which is low, medium, and high. So after converting these into three pairs or three values, we now have 9 sets of values corresponding to cell and pin density. uh, as an example, we have low, 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 medium, low, high, and so on, medium, medium. So we built different combinations of cell and pin density. We inculcated this information with floor plan, and we built a processed floor plan image. Now this processed floor plan image inculcates the information, or it inherits the information also depending upon the cell density and pin density. This processed floor plan image and congestion and the corresponding congestion image are mapped together, and then they are fed into the model of generator and discriminator to let it be learned. Now the model iterates over the dataset again and again to improve its accuracy. One major thing, or one important thing, is that we train single model for each metal layer. So there are multiple metal layers when we try to with respect to floor plan. So there could if I'm not wrong, so M1 to M4, M1 M5, M1 BA, I guess there are total of M1 to M7 metal layers. With the increase in number of metal layers, the corresponding congestion also decreases. So uh, as of now, we have trained our model on two metal layers, or on the congestion images of two metal layers, and they both are two separate models. How are we categorizing the cell and pin density? So in the previous slide, I mentioned that we categorized our cell and pin density to low, medium, and high. But how are we doing this? So from the domain side, we got to know that as the colors, okay, so you can see these colors as the colors move from left to right, the density of cells and pins increases. So we try to get the information from here. Basically, what we did, we visually analyzed the images and we put them into the bucket of low, medium, or high. So for example, this image, we categorized it as a high cell density image. Why? Because it has a very dominating yellow color and which lies toward the very right side of the bar. Similarly, this image was categorized as low pin density because it was containing a dominating blue color which lies towards the left bar. Now this image can be a bit tricky and it again depends upon judgment of particular person as well. So this image can be categorized as medium also and it can be categorized as high also. So we categorized it as a medium. Why? Because the green was much more dominating. Yes, there were few yellow pixels as well, but they were not concentrated as they were concentrated in this image. So this is how we categorized our images by looking into them visually. Mhm. So as I said that we then try to find out different combinations of cell pin density. So there are total of 9 combinations and we associate then a unique color to it. So just after we get the cell and pin density, we forget about what was the cell and pin density. Now we only consider what is the color that we have to give to them. So how we are pre-processing the floor plan? We take the original floor plan, we take the cell and pin density pair, and we add a solid border across the floor plan to tell the model that okay, this color belongs to this cell and pin density, and that's how we get our processed floor plan. Once our model is trained, the testing of the new floor plan, or I would say new design floor plan or new technology floor plan, that hardly takes any time. It takes just around 10 to 15 seconds of testing, and after that it will provide you with the probable congestion that we want to see, or the hotspot of congestion in the for the floor plan. So the user what user need to do is user need to provide a floor plan image, cell density as from low, medium, and high. That should be one of the parameter, and similarly the pin density. Once this is done, we take this, we pre-process our floor plan, do all the pre-processing that we did while we did the training. We feed it into our trained model, and afterwards we get our predicted congestion image. So basically, the complete EDA flow of, let's say, 2 days, 3 days of work now is being given to us in a matter of seconds. Again, I am not claiming that it will be 100% accurate, but it will still give you some hotspots or the areas where the designer needs to rework model performance. The solution that we used was actually a combination of supervised and unsupervised learning. What do we mean by supervised and unsupervised learning? In supervised learning, we have a trainer with us. We have uh, sample images on which the labels are already known. But for unsupervised learning, we have a huge bulk of data which do not have any labels and nothing at all. We just need to derive some information from it. But whereas for supervised, we already have the information and we want to make it learn to the computer or to the model. So there was no performance metrics that was easily available in the market. So we tried to came up with our own performance metrics. So we tried to do the same thing in two ways. So one was the manual feedback. what we did is we we provided uh, the experts within Infineon the actual congestion image and the model and the congestion image that was predicted by the model. Now they this pair was provided to them, and now they gave us feedback. Okay, that how good does it look? Is it very bad? Is it bad? Uh, the images really look alike. So we took their feedback and stored it in our database. The second concept or the main metrics that we came up with was the mean squared error. So here we did a bit different. What we did, we divided each this image into four color maps. The four color maps of red, green, yellow, and blue. We compared each color map with the corresponding predicted congestion image. Now, why we only choose these colors? Because these are the most dominating colors, and these are the colors that actually tells us about the congestion, that how how worse the congestion is or how good the congestion is. Um, so we extracted multiple color maps. We found out the mean square error between these color maps, and then based upon this mean square error, at the end of the day, we just get a single number out of it, and then based upon these numbers that we get, we built a qualitative range. The qualitative range looks like this, where we say that from 0 to 50, if the mean square error is less than 50 or lies between 50, it's an excellent prediction. If it is between 50 to 150, it's very good, and so on. uh, if we label, if the mean square error is more than 250, it's probably bad, and the prediction is not so good. Here you can see we tested on around 69, 70 odd test images or floor plan images, and we tried to plot the mean square error for each of the color map. The one good thing was that whenever there was a whenever the results were bad, then all the four color maps were actually giving bad results. It was not like just one floor plan was giving bad, one color map was giving bad results. All the four floor plans were giving bad results. So that worked in our favor, that okay, the overall picture looks good or bad. That depends on the entire picture, not just one color map. So finally, okay, sorry. After all these 69 or 70 odd floor plan testing, we achieved an overall accuracy of around 79%. So finally, to conclude the tutorial, we provide the user with best and worst case congestion. uh, the model accuracy is pretty significant, 80%. We do want to improve this accuracy much further by bringing in some rules, or maybe applying some different AI algorithms parallelly, so that they can assist another AI algorithm that we already built. The prediction time is significantly less. It's around 10 to 15 seconds. Again, this time, the prediction time can further be reduced based upon your hardware specifications. uh, this running time of 15 seconds or 10 seconds is on CPU. um, Prediction, we can definitely further improve the accuracy by identifying the congestion trigger points. More and more trigger point If we consider more and more trigger points of congestion, we can improve the accuracy much further. We also found out that the approach is pretty generic, and we can also apply the same applications towards other physical design domains as well. So am I okay? So I do have some still do have some time. So what I can do is I can show you a tutorial as well, or one short demo. So what we did is we built a website where, so this is for Infineon. This is not open to all as of now. So we built a website where the user just need to upload a floor plan and get the final results. So it will take just 10 to 15 seconds of time, and then it will display you the results. So okay, so here fed in a sub SRI3 uh, shape. You can see at the results page as well when the results will be displayed, and it is now predicting the congestion on it. So now why I particularly choose this image, because this image we have given to experts as well, and we have asked for their feedback, so we know that okay how the results looks like on this. Okay, so this was the floor plan, or I would say the chip that we fed into our that we uploaded, and these are the results that we are getting. So at the bottom of the screen, you can see that what were the combinations of cell and pin density were used. So this correspond to cell density as low and pin density as low. So basically, I would say this is the best congestion possible on this chip design. And similarly, on the very right hand side, we have cell and pin density, which correspond to high. So it says that it is the maximum congestion possible on this floor plan. And in between, the designer can experiment based upon cell density and pin density. So they can choose from low, medium, high, or whatever they want to find out. Um, a- uh, at first, we show the medium results. Uh, they can also change between the metal layers, on which metal layer they want to see the congestion, and so on. Now the feedback that we got, so again, the feedback that we got that this congestion should not have been there. So but the red hotspots, the worst congestion hotspots, are very correct. So in this high congestion, uh, in this worst case congestion, the hotspot that one can see on this intersections are pretty relevant, and these can also be seen in the actual congestion as well. Thank you. So with this, I conclude my tutorial. Please feel free to ask any questions. In case you want to contact us further, you can also contact us on these email IDs as well. Thank you. So are there any questions? Sorry, were my slides visible? So I got a message that uh, sorry, the tutorial, the window that I showed, was it visible? The demo that I gave.
It was visible. I can understand the question. It was visible, yes.
Okay, sorry. Thank you. So if there are not no any questions, then I would say thank you. Thank you all for listening.